Okay, thank you very much. I put there a very nice title following the tradition started by David of wonderful titles for this talk. So I put this on universality and in adaptive matter dynamics. So what I'm planning to do is to start simple and ask the question of how can we describe in very basic terms how adaptive matters moves, and see if we can go about how long can we go about in terms of describing patterns in nature. So let's see. We'll start by okay. So let me acknowledge first the help of these fellows here. Miguel Fuentes, which is a part of the external faculty of the Santa Fe Institute, and a physicist. Andy Romiger, a former student of John, also a postdoc now at Santa Fe, and he spent time in my lab a long time ago. And Rolando Rebolledo, who is a stochastic person, mathematician, and Mauricio Tejo, also a mathematician. So this is kind of a big crowd of people. Just to set the stage, what I'll be talking about is just realizing very simple fact that we are talking about the dynamics of a different state of matter, which I like to call adaptive matter, and we are going to try to develop a very simple theory for understanding its dynamics. So let me start with a simple relationship. And this is, as Brian and also John have shown, there are a lot of scaling patterns in ecology. One of the famous one is this species area curve. They give you the number of species, how it changes with the area of the system that you are measuring. This is very old stuff, comes from the work of Arrhenius in the 1920s, and it was luckily formalized into this theory, which is called the Theory of Island Biogeography, back in 1967, and this is the first book of this wonderful series of books in ecology. And basically it says that what is behind this relationship of how the number of species change with area is this master equation here, which just gives you how the probability of finding S species in a given community change through time. And it says that it's function of two rates, the rate of colonization and the rate of extinction, and that they have this kind of shape, and they sort of determine a distribution, an invariant distribution for this stochastic master equation here. And interestingly, MacArthur and Wilson never talk about this distribution. They never derive it. They just said it exists. They do some work about it, but never talk about the shape of this. But they just put out this master equation. So what happened next in this story is that neutral zero came about, and Hubble took that equation but made it the same at the level of individuals now, not the species. Okay? So the master equation is now for the probability of observing k species with n individuals. And it's exactly the same. Instead of colonization, you have birds. Instead of extinction, you have death. And they derive from here, making some assumptions like density independence in the case of these rates, they derive the Fisher-Log series distribution. And that's fine. But there is a little problem. They cannot be true at the same time, because the master equation for a species, it will be a function of the master equation for individuals, but it is not Markovian anymore, because you will have a large kind of vector of possibilities for the transition rate that will no longer be exponential. So there is a problem, and this is wonderful because you detected an anomaly, and things have to fit somehow the theory. So what is the solution to this? Well, go back to basics. And the basics is these fellows here. They developed diffusion processes. Well, pretty much Kolmogorov of Seward Wright developed what he called the integral equation for gene frequencies, which turned out to be very good approximation to diffusion processes kind of formalized by Kolmogorov. And Fisher also did an attempt that Seward Wright showed him that it was wrong, but it was close. So he was able to recover from that, I think, eventually. So basically what these fellows did in terms of diffusion approximation is to show that if you have a spatially structured community with infinite number of local populations, the distribution of gene frequencies is given by this equation, which is the beta distribution. So that's the way genes are distributed in terms of their abundance. We did the same for individuals, but making a little variant here. And the thing is that we took what we call an open system approach. We say, well, let's work with an infinite number of individuals in the system we call the focal system here, which is in this dotted line. It's just some scale that you define in the world and interacts with the rest of the world because of these arrows here. So these interactions are codified in the noises. So everything that you don't know that might be affecting your system is put in the noises. So the way you translate this into this open system approach into the equation is that you define the rates now, birth and death, as the birth, the typical one, plus a C term. That C term codifies that interaction with the environment, everything that you don't know that might be affecting your system. The same thing with the death rate. So to some extent, just because of this is not truly neutral. So because it encompasses all interaction that might affect birth and death, and that like density dependence interactions with other species, so on and so forth. So it can be shown that this satisfies this stochastic differential equation. Look at the interesting part here is that the C terms end up in the coefficient of the Brownian. So it really quantifies the impact of the interaction with the environment. So this is followed by this Fokker-Plan equation that in the time limits actually gives you this invariant distribution, which turned out to be a beta distribution. But now we are not working with number of individuals, we are working with the proportions of individuals. This is the trick. It fits known distributions of plants, animal, insects, as well as the classical neutral theory, but this is based on kind of a diffusion approximation. And the nice thing is that it integrates the phenomenology of genes with the phenomenology of individuals within systems. And we have shown also that it works also for the distribution of richness. That is the distribution of number of species along communities. So it potentially unifies the three levels of organization. So let me shift gears now and stretch this analogy a little bit further. And to do that, I want to show you that the Brownian approach to the dynamics of adaptive matters, it might go a little bit further to understand macroevolutionary patterns. And if we envision this that evolution takes place on this fitness landscape, and if you have different fitness peak in this adaptive landscape, we will develop a model for a Brownian exploration of this landscape and how that actually can account for the fluctuation dynamics that you see in the fossil record. And the theory we will use is called superstatistics. And basically it says that you have an ensemble of systems, each one in a local kind of equilibrium, but they interact. And there is a particle following this, Langevin equation here that moves around the system, and in each part it have a different fluctuation dynamics. So the intensity of fluctuations changes from system to subsystem, and that intensity of fluctuation in terms of the fossil record is pretty much the extinction speciation dynamics of the system. So each of these areas are akin to, we'll say, peaks in the fitness landscape. And there is this adaptive matter particle moving around and fluctuating at different rates in the system. And we claim that the system that it has in each subsystem it can be well described by Brownian motion. Doing that, I'm making three more assumptions that we know they are pretty much right. If we assume, for example, niche conservatism, which is the tendency for entities to preserve their adaptation to the niche, if we also claim that there are some niche shifts which are associated to adaptive diversification, and we also allow for different niches or spaces in this adaptive landscape to have different volatilities in terms of the intensity of fluctuation, we can go and test this in the fossil record of the last 600 million years. And we show very briefly here that, in fact, the fluctuations within each family, order, and classes follow this kind of Brownian dynamics, that the volatilities follow a gamma distribution, and that if you put all of them together, all the fluctuations, you get a power law at the level of families and orders. So, just closing, what we have shown so far is that genes, individuals, and species seem to obey the same probability law. That's a beta distribution, and that at the macroevolutionary level, richness fluctuations are Brownian, depending on where in the different, with different volatilities, depending on the location within this fitness landscape. So, thank you very much.